Line 1 Dynamics example 16. Again, this is a connected particles situation. I've read through the question and I've labelled on the diagram all the different forces that are acting here. Friction on the rough plane, a normal reaction, the weight of this particle, and I've labelled here the angle alpha, which we know is the same as the one at the bottom of the slope. Tension in both parts of the string, and the weight. And I know that when this is released rest, this particle P will slide up the plane and particle Q will head down towards the floor. I've also drawn a little diagram because we know tan alpha is 0.75, which is 3/4. And we've done this on a previous question where we draw a little triangle. Tan is opposite over adjacent, opposite, adjacent. By Pythagoras, we know the hypotenuse will be 5. It's a 3, 4, 5 triangle. So if we need them in the question, we know that sine alpha, sine is opposite over hypotenuse, and cos alpha is adjacent over hypotenuse, so that's 4/5. So I've prepared the question before I've actually even read what we're being asked to work out. So first we've got to find the acceleration of the system. And I know that at some point I'm going to need to work out this friction, so I think I'll do that first. Vertically for particle P, well, parallel to the plane I should say, we've got R equals 5g, and because we're turning through the force, through the angle, sorry, it's cos alpha. 5g multiplied by 4/5, we know cos alpha is 4/5. 5's will cancel, so the normal reaction is 4g. That means that the frictional force will be 0.2 multiplied by 4g, it's mu r. So that would be 0.8g. So going ahead and actually doing the question, if we do F equals ma for this P, first of all, so for P, up the plane we've got the tension, down the plane we've got the friction, which is 0.8g, and we've also got a component of this force here, the weight, acting down the plane. And that will be 5g, we're turning away from the angle, so that will be sine alpha. That will be equal to the mass, which is 5, multiplied by the acceleration, which at this stage we don't know. So substituting in, we know that sine alpha is 3/5, so I'll sub that in there. And now I'll do a little bit of tidying up. So we've got minus 0.8g, 5's cancel, so we've got minus 3g equals 5a. And so one last step, t minus 3.8g equals 5a. So that's one equation. That's for particle P. I'm going to do the same for particle Q, which is a little bit simpler. Obviously Q is moving downwards towards the ground, so I'm going to do F equals ma downwards, direction of motion. So for Q, we've got 10g acting down, the tension acting upwards, and that will be equal to 10a. So that's equation 2. So looking at the two equations, same thing again, we have a positive t and negative t. So if I do equation 1 add equation 2, the t's will cancel out. And on the left hand side, I'm going to have 10g and a minus 3.8g. And on the right hand side, I'm going to have 15a. So 6.2g equals 15a. And if you put that into your calculator, a works out to be, let's do it as a fraction, 31 over 75. If you do 6.2 over 15 on your calculator, if it has a fraction facility, it will come out exact. If it doesn't, you may have got something like 4.05 as your answer. Now the second part of the question asks us to find the tension, so all we need to do is substitute back into one of the two equations. Doesn't matter which one we do. Given that t is positive in equation 1, I'll probably use equation 1. So t will be equal to, bringing the 3.8g over to the right hand side, 3.8g plus 5 multiplied by the full answer for the acceleration. And if you put all that in your calculator, it works out to be around about 57.5, but because we're doing two significant figures, if you look at your calculator screen to 2SF, it actually works out to be 57 newtons.